session brought to you by Save on Energy, and the Estimating Project Savings webinar series is on compressed air projects. My name is Nick DL. I'm an energy coach at Goldman. I'm really excited to talk about estimating savings for compressed air energy savings projects. And the theme is kind of for situations where you're working with less than perfect information, which we figure is always. Today we have Ron Marshall here with us, owner-operator of Marshall Compressed Air Consulting and trainer extraordinaire. I'm going to start us off and then hand things over to Ron for the bulk of today's session. This session is going to be recorded, and that recording, along with training materials, will be available on the new training and support page on the Save on Energy website. We will provide the link in the chat. Also, coming to you through the chat is today's participant workbook. You should be able to download that from there. You can use this to follow along in today's session, make some notes. It contains a key summary of the information we're going to cover today, and you can keep that as reference for afterwards. Link to that will be in the chat, like I said. So we have a three-part agenda for today's workshop. I'm going to start us off with number one, agenda item number one, which is just some good practices, standard practices for estimating savings. These apply to compressed air. These apply to other motor-driven systems, if not all electricity or all energy savings projects, or perhaps all efficiency and reductions type projects. Then I'm going to hand things over to Ron, who's going to start with some compressed air fundamentals before getting into estimating project savings. And within that section, we'll be covering a lot on good practices for and examples for baseline development. Part 4, I said it's a three-part agenda, but there is part 4, which is not listed here. That is the question and answer session. So we're planning to save up to 30 minutes for you to ask your questions, specific compressed air project questions to have answered by our subject matter expert here today. So we do encourage some interaction through the workshop, but if it's a specific question, we'd ask you to save it for the Q&A at the end. Okay, let me get into some good practices for estimating savings. So we've got 5 items listed here. There's probably more, but this is what we think is a good way to summarize these key items. So first, we want to start with considering how accurate your estimate needs to be. There's a variety of reasons for which you need to estimate your savings between just justifying that an opportunity is worth a closer look, all the way to making the final decision for capital investment. The next item that we'll go to, which is directly related to this, is assessing the data that's available to you, which will have a significant influence on how much effort to put into your estimate or how to approach your savings estimate. Item 3, this is probably can't be repeated enough, is to just always make sure you start by considering the baseline, developing a good baseline before you estimate your savings, and we'll provide a rationale for that. After that, we're looking at understanding the mechanism of savings. How do we save energy at a kind of more fundamental level within a compressed air system? And finally, understanding the calculation methods, tools, rules of thumb, and the respective limitations of those. So starting with appropriate accuracy, this chart is purely for illustrative purposes. In reality, the curve would be different for each unique situation. I happen to think this curve could or can be steeper if you make the best use of the data available to you, meaning you can get more than 60% of the way towards perfect accuracy for 20% of the effort as a thumb wag estimate. As I said, it differs, but the point here is that depending on what decision you're trying to make and the risks associated with that, you need to consider how much effort you should put into developing your estimate and how accurate it needs to be. So some examples, if you're getting ready to convince the decision makers in your organization to make a capital investment, then that's probably the situation where you want the highest accuracy. And because the downside, the risk, is your project underperforms and you stake your reputation in what might turn out to be a poor investment or the wrong solution. As we go down that kind of decision or risk threshold, though, the other reason you might be developing an estimate is to just proceed with further study, where the outcome might determine that the project's not viable. So the level of consequence is diminished. And then for operational changes, you might have a situation where you're just trying to justify whether you should trial a change in operations, and a change that is completely reversible. So there's perhaps some lost effort and some lost time, but otherwise reversible. And in such a situation, the insinuation here is that you shouldn't spend too much time on the worrying too much about the accuracy if it's something you can get to through trial and error, trial and reverse. This point kind of marries up perfectly with the next in our 5-point list of, and I made this point of if you make best use of the data available to you. So the secondary point there is to, before you embark on perhaps some a significant effort in collecting data or spending money on buying meters, renting meters to collect data, and or jumping right into your calculations, is to take stock of the data that you have available or proxy data that you can use to improve your estimates, to see what's available to you that can maybe get you to that threshold of accuracy that you're looking for. The next item was, making sure to develop a good baseline. So here again, an illustrative example where we say we have a project that's going to save 25% on a 100 horsepower compressor. If we just punch that into nameplate numbers, you can see that scenario on the left, and we'd come up with this savings number real quick. However, perhaps either through data available or just better, more conservative estimates, we would ask ourselves, how's that motor really running? How loaded is it? What's the duty cycle of this system? How does it run? Does it shut down on weekends or other periods? And come up with some numbers like an 85% load factor and an 80% duty cycle in terms of the number of hours it's operating. And so that same 25% starts to look like a lot less savings. So the cautionary tale here is that even if your savings estimates are perfectly accurate, if you don't start with the right baseline, you're bound to end up with an error, with a inaccurate estimate. Okay, mechanisms of savings. Understanding how your project is going to save energy really boils down to 3 or 4 things when we're talking about compressed air. All savings projects are either resulting from a reduction in airflow, a reduction of system pressure, an increase in the supply of compressed air efficiency, or the heat recovery from that equipment. I say 3 or 4 because depending on how you draw the boundary of the system, you can look at that heat recovery as part of improving the overall efficiency of the system. So we believe that understanding these mechanisms of savings is critical to not only identifying wasted energy and therefore opportunities, but also helps you come up with good savings estimates by understanding what it is you're doing that is expected to result in, at the end of the line, a reduction in the input power, the motor to your compressor. So Ron's going to go over a handful of compressed air project savings examples, including the calculations methods and their limitations, and walk through some worked examples of these project examples. So without further ado, I'm going to hand things over to Ron. Ron is a Master Compressed Air Challenge instructor and consultant. He's worked in the business for many years, as you can see, level 2 instructor with Compressed Air Challenge and an international trainer. You can see he doesn't just talk the talk, but he walks the walk with many, many clients over the years with successful project implementations. So with that, I'd like to introduce Ron, and I'm going to quickly switch screens so that he can
Or
take over
yeah,
and control.
I'll try to take over. Can I just click my share?
You bet.
Okay. It usually takes my computer a little bit to decide what to show. How's it look?
Great.
Okay, super. Yeah. So you're probably wondering why this badge is here. So I'm the marshal, of course. The compressed air marshal. People make fun of my name, and I figure I can use that. I can even use that internationally because people from Malaysia have heard about Westerns, right? They've watched them for very many years. So I tell them that I'm the marshal. I go around from town to town saving people from the criminals that might abuse compressed air and run their air compressors unwisely, right? And instead of a white hat, I have a hard hat. Instead of a 6-shooter, I carry around a leak detector gun, right? So I can use those tools to help people optimize their compressed air systems. All right, so looking at a compressed air system, we want to look on both the supply and the demand, as Nick had mentioned, right? That's where some energy savings lie, right? And it depends on the facility where the most savings potentials are, right? So the supply side, we got air compressors, we've got receivers, we've got air dryers, pressure gauge. Good to be measuring pressure, not only at this point, but very many spots, right? Dry receiver. And if you're lucky, the plant has a flow meter that makes measuring leaks and things like that really easy. On the demand side, right, we might have a piping distribution system. It could be way more complex than this. This is a really good loop system, right? We've got some significant end users. It looks like maybe that end use might be pressure critical, right? It's a complex piece of equipment, right? And that might be causing the pressure to be too high. Uh, Even I have a booster compressor here. And uses, pressure regulators, we call them FRLs, filter regulator lubricators sometimes. Very often, right there is where the biggest pressure drop in the plant is and should be investigated. We've got condensate drains. If the piping gets full of water, that may or may not be efficient. And we have shutoff valves. Wow, those things could be used to shut off the flow of compressed air when airflow is not required, right? Types of compressors that we see in the systems, right? We've got rotary screw compressors, reciprocating compressors, rotary vane. Those are what we call positive displacement. So for every revolution of the shaft, they produce about the same amount of CFM, right? And we might have axial and centrifugal compressors, right? They're dynamic compressors. So every revolution of the shaft does not produce the same amount of air. So they're kind of different animals, right? So these are quite interesting pictures. You may not see compressors like this in your plant. You might just see like one of those green or blue or white colored boxes, right, with the compressor components right in it. All right. Compressors can be controlled in North America here. There's quite a few different modes of operation for compressors controlled, right? Compressors need to be controlled because if you turned on a compressor and it put out 100% of its output all the time, right? And you didn't need that air, what happens is the system fills up with air and the pressure starts rising until something pops, right? So there's a need to control the compressor. So if you had 1,000 CFM compressor and only 500 CFM of load, you somehow have to get that compressor. It may be the only one you have, right, to put out 500 CFM, right? So there's different modes of operation. One is modulation, One mode is load unload. Could be variable displacement compressors, right? Variable displacement and modulation are kind of a North American phenomenon. You'd never see any of those, or hardly ever anyway, in Asia or Europe, right? The Europeans learned a long time ago because their power prices are so much more expensive to run the compressors more efficiently. And we've got here variable speed, right? And what these lines are trying to tell us, right? We've got input power here and flow capacity here. It's trying to tell us how much the power will reduce as you start to part load that compressor, right? So if you're interested in having your supply side running at maximum efficiency, you'd want to choose a mode of operation for your trim compressor if there's only one, or trim compressor if there's multiple compressors, right? The one that's taking the partial load, you want to choose the one that's the best, right? One that's closest to a perfect compressor, which would be a one-to-one turn down from 100% flow, 100% power, all the way down to zero. So it looks like in this chart, variable speed with stopping would be the one that more closely approximates the one-to-one turn down, and the worst one would be modulation, right? And I'll show you an example of modulation a little bit later in the slideshow, right? So you need to know how the compressors are controlled, and it's not just single compressors, right? There could be a multiple system of multiple compressors operating together, right, in a coordinated fashion, right? So, establishing compressed air baselines, that's the first thing you should do, right? In looking at your system, if you're initially starting out to try to figure out how to improve the energy efficiency of your system, or uh, solve other problems as well, you need to measure something, right? Measure. So the premise of the workshop, right, is to help you estimate the savings, maybe using simplistic calculations if there's very little information available. Um, you might have amps, you might have pressure, you might have characteristic curves, right? And you might only have compressor status, right? Whether it's loaded or unloaded for periods of time, right? Use that information to be able to estimate if there's some significant potential for you to uh, capture in improving your system, right? So the really simplistic way to estimate power and energy consumption of a running compressor is this formula right here, right? So the power, motor power, horsepower nameplate divided by 746, right? So there's 746 watts per horsepower, right? And then multiply by a load factor. You might put an ammeter on the compressor and find that 100 horse compressor, right, is supposed to be drawing 100 amps at 600 volts, right? Is only drawing 85 amps. So you could calculate a load factor and use that to estimate the average power on the system, right? Very simplistic, using kind of a single point to estimate what the power consumption might be. And then if you know the operating time for the compressor during the year, right, you can project that forward, assuming that the compressor's in the same condition throughout the year, right, and multiply, who knows, by 8760 or something and calculate kilowatt hours. And then you could take the kilowatt hours, multiply it by your electricity rate, and come out with the operating cost of one or more compressors using that simplistic method. Um, I like to at least have my clients, or when I'm doing a study, measure the amps, right, of the air compressors in a system, right? And we can use this equation, right? Volts times amps times power factor times the square root of 3 divided by 1,000, right? And that will give us the power conversion from amps to power, right? So um, we're talking about three-phase power, right? It could be single phase too, voltage line to line, right? And the average amps of the three phases, right? And the power factor is the most difficult to get because it's okay at full load, right? It'll say right on the motor usually what the power factor of the motor would be at full load. But as the compressor comes down in load factor, the power factor changes. So if it's a load unload compressor, it's spending a long period of time in unloaded condition. If you're assuming, say, the motor nameplate says 85%, if you're assuming 85% for all that significant unloaded power, you'll be making a significant error in your calculations because an unloaded compressor doesn't have an 85% power factor. The power factor might be as low as 20-25% in that unloaded condition, depending on the size of the motor and the load on it during unload power consumption. So the next chart is just a snapshot of a load unload compressor, right? It's just amps and power, or sorry, kVA and kilowatts, right? So we can see here, here's the kVA, right? Not including the power factor in the calculations. And here's the kilowatts. So 85% power factor here, 57% power factor here. So if this compressor had a long period of unloaded runtime, your calculations would be incorrect, right? And that's one of the reasons why a project might underperform, right? If the calculations are not done correctly. All right, one really nice set of resources for estimating power, especially with and this particular sheet is from a variable speed drive compressor, is Compressed Air and Gas Institute, CAGI. I'm going to call it CAGI. That's what I mean when I say CAGI sheets, right? So CAGI developed a standard reporting format for various different types of modes of compressors, right? So they have for fixed speed compressors, they have for variable displacement compressors, they have for VSD compressors. And this particular one is a VSD compressor, and you can see the reporting sheets shows you the pressure at which this compressor is tested, its nominal horsepower rating, and then we can see for various power, it shows the capacity output for the compressor, and this could be used by somebody in calculating what the flow output might be at the in various input powers you might capture when you're doing data logging. Now, it's important to know that this has to be adjusted for pressure, right? Because this compressor here is been tested at 138 psi when you might be running this compressor at 100, right? So there's a difference of 38 psi. And as we'll learn in the next few slides, the power consumption of a compressor per unit output increases 1% for every 2 psi increased discharge pressure. So you have to, if you're running at lower pressure than and this test pressure, then you have to adjust, right? One thing here, isentropic efficiency, that takes the pressure adjustment away when you're comparing compressors, right? So if you are comparing 2, 3, 4 compressors, you want to know which one is most efficient. They're tested at different pressures, right? You can take a look at the isentropic efficiency, and that's telling you out of 100% how efficient this compressor is. So it's 82.95 out of 100. That's a really efficient compressor, right? A very efficient compressor and a nice curve on it, right? Pretty flat for a variable speed drive compressor. So very useful for new compressors. There's KGI sheets available widely. The major manufacturers, anybody that's part of the third-party verification program of KGI must publish accurate sheets for their compressors. All right, so operating hours considerations. So um, in a system, the compressed air system is not necessarily 100% of the time, right? And we can see here in this time-based chart, they turn off the system at night and on weekends, right? So the compressed air system is only operating a fraction of the 8760 hours per year. There's sometimes seasonal duty that affects, sometimes there's an extra shift in the summertime or when berries are ripe and all that stuff. There's statutory holidays to figure out. There's plant shutdowns. Some plants shut down 2 times a year for two weeks, right? And that'll affect your operating cost calculations, right? Um, Non-operating modes, common for one or more compressors to run, often mostly to feed leaks. So this particular time-based chart is showing the compressed air system shut off. That's a really good operating practice, right? And look at this. Through the weekend, the pressure didn't even get to zero yet. This is a very, very tight system. The person operating this plant should be given an commendation for really good leak repair practice, right? All right. So yeah, so if we wanted to do leak testing, and we're going to talk about that a little bit later, we would be maybe doing it at the end of a shift or on the weekend or something like that. And sometimes compressors are left on when they're not required, right? So one plant that I recently went into, they only have an 8-hour shift, don't work on the weekends, but yet they leave the compressed air system on 24/7 even during holidays, right? And I calculated what the waste of that system is. 98% of all the air going into that plant is wasted because they leave the compressors on. So very nasty, right? Uh, Waste level in that plant because they really didn't get the memo, right? And they left their compressors on. All right, determining a baseline, a good practice of doing a baseline, minimum 1 week of measurement, right? Because there's those weekly shift-oriented type of things and with weekends, right? And we can see here this particular data visualization program is showing Monday, Wednesday, Tuesday, Thursday, Friday, Saturday. Here, a little bit of production and Sunday, right? Where there's really not much production at all, right? And visualizing is pretty important. Sorry about that. I had a virus over the weekend and I might be coughing a little bit. Pregnant pause. All right, so good way to visualize, right? So we can see here the week time, we could average all those weekdays and do something special with the weekend activities, right? Here's another way of visualizing it, right? We can see, and this is, we're adding up compressors, right? We can see compressors and we're even including the dryers in the power consumption and seeing how that correlates to airflow, right? And we can see the power and the airflow are really one on top of another. So this is actually a really good, really efficient system that turns itself down in a one-to-one ratio, right, with the reduction in flow. Um, Reason being, it's got a really big VSD compressor running. Here's a way to visualize, multiple compressors in a system. And it's very easy to do. This is a visualization program that I had used way back when, and it just takes the data from a time-based plot, right? Dumps the data into a spreadsheet, sorts it high to low, and we can see the load duration of the compressor. So this compressor really efficient, right? It's fully loaded all the time. This compressor's got a little bit of unloaded runtime. This compressor, a lot of unloaded runtime. And we even have the air dryers. So one of these air dryers is a cycling dryer. So we can see that it turns itself down quite nicely, right? In relation to the flow, right? So we can even identify that the compressors in all cases here are fixed speed compressors, load unload controls based on the shape of the curve, right? So it's just a way to visualize the duty cycle of a compressor. So we can use these duty cycles. We can calculate if these days, right, are average, right? We can calculate from this the flow, right? We could do the flow, we can calculate the kilowatts, all kinds of good things, right? So we might identify some similar days from that previous chart and take that and say, okay, all those days, Monday to Friday, are production days, right? There's estimated 6,000 hours in a year of those days at various CFM and kilowatt, right? We can calculate, project forward. We're not measuring for a full year, right? But we're measuring for 1 or 2 weeks and projecting forward. Take the weekends to figure out how many weekends the system is operating and calculate the baseline, right? The baseline costs, the baseline flow, the baseline peak and average kilowatts. And here's just the more detail in breaking down what's happening in the day types, Monday to Friday and Saturday and Sunday. For this is a much bigger system, right? That we might use that to calculate what's happening on a system. All right, determining the baseline, some alternate methods, right? And this is the first thing I go to if I encounter a system that's running a load unload. I'll go to the compressor hour meters, right? Most modern compressors have hour meters that track the running and loaded hours, right? And I take a look at the ratio of loaded hours to the running hours, and I see that loaded hours are a small percentage, right? That tells me it's telling me the compressor status, right? Loaded or running, right? And I can see from that that this compressor is very inefficient because it has quite a few unloaded hours, right? For a lubricated screw compressor, the unloaded power consumption is about 25 to 35% of the full load power, right? And that's wasted power if you leave the compressor running unloaded for too long, right? Because it's not producing any air, right? So um, this one has not very many hours, right? Less than a year's worth of operation. So who knows whether that's true or not for when we're looking at it. So usually what I do is I would take the hours 1 week, say on a Monday at 8 a.m., let the system run for a couple of weeks and then take the readings again. And that gives me the ratio of loaded versus running hours in that period of time that's most recent, because this is through the lifetime of the compressor. Who knows, this compressor could have been running for a year in a shutdown plant right before they commissioned their production facilities. All right, so estimating flow from compressor status, and this is done by the compressor suppliers too. There's some suppliers that just hook a meter up to either monitor whether the compressor is loaded versus unloaded on the load solenoid, right? And so when I sorted this high to low, I can see this particular compressor has been loaded for 40% of the hours, unloaded for 21% of the hours, and off for 39% of the hours, right? So I can see the duty cycle of that particular compressor. If I know the power, I can calculate the power consumption, the wasted power here in the unloaded condition. There might be something I can do about that, and I can calculate the flow, right? So this compressor, very small compressor. We're talking about small systems, and I see somebody from Toyota is here. This would be like a tiny, tiny little compressor for those guys. But you could add zeros. It's all the same, right? It really doesn't matter about size, right? So 100 CFM compressor. Find the average flow in this period of time, right? All this here, 40 CFM. But the system is shut down and we might want the average flow in here only, right? And we would, because it's running 61% of the time, we just take that 40 divided by 61%. So the compressor within this period of time when the system is active and pressurized would be running on putting out on average 66 CFM if it was running at its rated output. Usually um, positive displacement compressors will be putting out pretty close to what their nameplate says. Estimating flow of from compressor status, load duration plots. So that's what I call these, right? Calculating flow in each segment. So we could calculate the flow in each segment throughout here, the loaded portions only, right? And we could use flows from KGI sheets too, and characteristic curves. So I can take a look at this. As I said, I can tell what kind of compressor it is. This red one is a VSD, so this is fully loaded VSD. This is in its regulating range. This is at minimum speed, and this is when it unloads to shut off. These two compressors are actually positive displacement compressors, so there's some modulation with positive displacement, and here's unloaded, unloaded. And what's this? This compressor is running unloaded, not doing anything, right, through a long period of time. So that tells me that there's something that could be done about perhaps through control, and we'll get into an example in the later slides, right? Estimating power from compressor status. So using load duration plots, we can calculate flow and power in each segment for each compressor, multiply them out and add them together. We could use rated flows from KGI sheets, right, to help us with calculation and determine whether the mode of operation of each compressor, modulation, variable capacity control, load unload, or VSD. And this is just a calculation from a spreadsheet that you could even make yourself, right? Where I broke down all those curves in the previous site, and the first two sections are just calculating the flow output for the fully loaded portion. There's a portion between loaded and unloaded where the compressor is transitioning between the two, and then unloaded, right? And it just adds them all up together and comes out with a average system kilowatt and CFM for each compressor on that curve. All right. So that's understanding the baseline and how simplistic methods could be used to calculate the baseline. We want to take a look at the waste now, the system waste, right? So very typically, there's a recommendation to find your baseline leakage, and may not necessarily be only leakage flow. It could be leakage flow and critical users maybe that have to be left on, like a fire system or something like that. But this this is widely described. You can find it all over the internet. kind of a blowdown test, right? Where you can calculate the leakage if you know your volume in cubic feet, right? Of your system, right? Total system. That's a hard thing to do in a large plant to calculate that, but there are tools available to help you do that, add up all the storage receivers, the piping volume and stuff like that. In this case, this formula, we're talking about cubic feet, right? We might have storage tanks that are in gallons, right? In the compressed air world, the gallons that we're talking about are not Canadian imperial gallons, right? They're US gallons. So we have to make sure that we know the difference. So if we know our system volume, we know the during the test, we turn off the compressors, allow the pressure to drop right between this pressure and this pressure, record the time. If we know the ambient pressure, we can calculate from the drawdown of the pressure how many CFM is flowing in that system, right? So to estimate leak flow. We can also calculate leak flow using a cycle timing test. I always jokingly tell people that it's a magic formula, magic equation. You just wave your hand over your air compressor and look at your watch, right? You're turning a running compressor into a flow meter, right? So you basically just on the weekend or something like that, you do a special test. You're running one compressor only, right? You time the load and unload cycles. It has to be a load unload compressor, right? And you might find 1 minute of loaded activity and 7 minutes of unloaded activity during the weekend, and you just take the 1 minute and total cycle time comes out to 12.5%. This compressor is 500 CFM times 12.5%. 62 CFM is the leakage rate. Now, I personally don't like going to a plant on the weekend and doing this test because I'd rather be playing golf, right, on the weekend, not in a dirty old industrial plant. So I would rather put my data loggers on and do this test later, right? Because you can pick all this stuff off at data logging, right? If you're measuring pressure. Okay, let's look at air savings now. Air savings, right? Compressed air project savings optimization occurs when we improve the efficiency of the compressed air production, right? So we might do that by replacing the compressor with a more efficient, or getting it to operate a little bit better. Or it doesn't necessarily have to be compressor. It could be something that's done about an air dryer, right? If it's a more efficient air dryer, refrigerant or desiccant. If we produce less compressed air, and if we use the heat of compression, right? Heat of compression, the most energy that comes out of the air compressor is not the energy in the compressed air, it's the heat coming out of the air. So if we can use that, and very often industrial plants have too much heat, but sometimes you can use that heat and recover it, say to displace natural gas heat or something like that in the wintertime. So where do we look, right? Where do we start for systems? We might reduce the pressure, optimize compressor controls, recover compressor heat. We might use more efficient dryers, like cycling style instead of non-cycling. Put in a very large receiver, right? My rule of thumb is if somebody walks into your compressor room and doesn't do a double take when he looks at your large air receiver or your control receiver, if he's not surprised, then it's probably not big enough, right? Significant size, especially if you have load unload compressors. Fix air leaks, properly size pipes and hoses to get rid of pressure loss. We call it in the industry the dirty 30, right? The last 30 feet of pipe is usually where the biggest pressure loss is, right? And if you don't address that pressure loss right at the end use, what happens is the compressors must run at a higher pressure, right? And they waste energy. avoid inappropriate and unregulated uses, right? So we should be looking at, when we're trying to optimize or reduce the operating cost of a system, we should be looking at both the demand side and the supply side and how they interact, right? Taking the systems approach, right? So we might assess, right? We look at and this is usually where the first step is, looking at how well the compressors are operating, right? Um, it's a controversial issue because people in the industry say that you should start at the far end and work back, right? Try to reduce the air demand, waste, but looking at the supply efficiency, reducing pressure, and reducing air demand. So assess how the system is working in all those categories and act, right? Reduce, and this is the systems approach, reduce the air demand, reduce pressure where possible, and better control your compressors at a lower pressure. Estimating savings, leak repair, right? So the mechanism of saving, we're reducing the airflow. The control signal cuts back that compressor output depending on how it's operating, right? Operating mode reduces the air production on that compressor, right? And reduces the input power in some manner, depending on the curve that compressor is operating with. Um, some methods of detecting leaks, right? We might go around with a ultrasonic gun, record decimal readings, right, on things, and try to estimate the CFM of the leaks, right? Find all the leaks, make a report, make some work orders, right? Get people to fix them. Uh, if you're lucky enough to have a flow meter, you don't even have to do the calculations that I just described in a few slides ago, right? You can take a look at what the flow is during the weekend, right, on that flow meter if it's got a display, right? Uh, Pressure drawdown or cycling test, we describe that. And we need to determine if we want to know what the leak repair economics is, we need to know what the system's specific power is, right? How many kilowatts per 100 CFM those compressors operate at, right? And poorly controlled systems, this is a pitfall, like a modulating compressor, don't react to very nicely to flow reductions, right? So in modulation control, it's only about 3% reduction in power for every 10% reduction in flow, right? So you're not getting the biggest benefit from your efforts, right? And here's an example here. So this is a modulation curve. We can see every 10% reduction, we only get a 3% reduction in power in this range here. So let's estimate, okay, modulating system, operating at 2000 CFM, 450 kilowatts. Estimated leak rate, we've done the testing, 250 CFM. Let's assume fixing 80% of the leaks. That's a large effort, right? We're down to, that means we've saved 200 CFM of leaks. Typical loading is between 85 and 100, right? And as per the characteristic curve we can plot, we can see the red arrow there. It's telling us that for 10% flow reduction, we only get 3% power reduction, right? We're only getting from our efforts 200 CFM of leak repair, only 15 kilowatts of repair. The system specific efficiency, overall is 22.5 kilowatts, but the effective uh, leak reduction, because the system has a poor turn down, is only 7.5 kilowatts for every 100 CFM reduction, right? So that's what happens when you don't have good control of the compressors. You don't have anywhere close to the 1-to-1 ratio that we would like to see for a perfect compressor, right? Okay, we might want to reduce the discharge pressure now, right? So mechanism of savings, we reduce the discharge pressure, and we have to do some research to make sure that we're not causing problems downstream, right? It reduces the work to produce the same volume of air, right? So that's the for every 2 psi reduction at the discharge of the compressor. Um, and this is in a range between 80 and 120, right? It's kind of a rule of thumb. There's more accurate ways to estimate, right? If you dig into the engineering calculations, but very easy to remember. Uh, so with the reduction in pressure, it reduces the input power, right, of the compressors, right, for the same CFM output, right? Pitfalls, we have to make sure that things can run at lower pressure. Sometimes the dryer might be overloaded if we go too low, right? Dryers are also affected by pressure. And it reduces the loaded kilowatts only. Bear with me for a sec. So here's this is what I call banana curves, right? I jokingly think this is a banana, but load unload compressors have these different curves depending on the volume of storage that's connected to them, right? And uh, we would when we're reducing the discharge pressure, only this end increases or decreases, right? Not this end, right? And these curves represent the average kilowatts or percentage kilowatts for various loading conditions, right? The compressor, if it's a load on compressor, it's jumping from 100% down to 0, 100%, 0. And if we plot it out at 40% with small storage, the average power will be here. 40% with large storage, the average power would be here. So it's jumping back and forth, but and we plot out these banana curves, right? So we can see what happens if the pressure increases or decreases at 100% flow. You get the maximum power savings, right? But if this compressor is running down here, we don't get all that much power savings, right? Because it's closer to the end that doesn't change, right? The kilowatts does not change in the unloaded condition, even if you reduce the discharge pressure. All right, pressure reduction example, right? And we've seen this chart before, right? Fully loaded, the average power in this condition, 19 kilowatts. Unloaded, if we take into account, and this is amps, right? We're taking into account the power factor, it's only 9 kilowatts here. So 15 psi pressure reduction results in what, 7.5% reduction in power, right? Unloaded power remains unchanged, this portion here. So the 19 kilowatts times 7.5%, right? Only 1.43 kilowatts. In the 40% portion that this thing is running fully loaded. So on average through the whole period, we're saving about half or 0.6 kilowatts, right? Now, if you reduce the pressure, in theory, if you've got lots of unregulated use, the flow will go down in the plant as well. In this case, I'm not using that savings for this example, right? Now, this is a very small compressor, right? But you could add zeros to the size of the compressor, and it's the same principle with larger compressors as well. More efficient compressors. So older compressors that are out there running are old designs, are worn out inside, right? And if it's time to replace them, there might be some pretty significant maintenance costs associated with an old compressor. The newer compressors are, especially once they started publishing these CAGI sheets where people could compare between the compressors, the manufacturers have all started to optimize their compressor designs, reducing the internal pressure drops, adding much more efficient motors, optimizing the screws, all that stuff. So it may be that you need to replace a compressor, and this is a really good way to make your production side of the compressor more efficient, right? So um, if you if you want to calculate the savings, you're basically just taking a look at the KGI sheet of the new compressor, right? Might be quite a quite a bit lower kilowatts per 100 CFM as the old compressor, right? And you're calculating the power savings by comparing the existing compressor to the new compressor with the new kilowatts per 100 CFM, new curves using the KGI sheets, right? Pitfalls, you have to adjust the KGI sheets for discharge pressure compared to the test pressure. The factor for slope intercept for a characteristic curve varies with the storage capacity, right? So if you take a look at a KGI sheet for a fixed speed compressor, it only shows the specific power fully loaded, right? So you gotta kind of work back into those banana curves, those curves, depending on the storage volume, right? That's connected to the compressor, and estimate, what the power consumption might be. Say if this new compressor's running on average 50%, right? Take a look at the curves, take a look at how many gallons of storage you have, and estimate the savings accordingly, right? So the reason it's kind of complicated, but the load unload compressors, they work on those, they're not linear, they work on those curves, right? If you had a variable speed drive compressor now, replacing a fixed speed compressor, quite easy to calculate what the new kilowatts would be. And we have an example coming up for that, right? All right, baseline, more efficient compressor example, right? We've got these average flows, average power, right? The system's running at 40 kilowatts per 100 CFM, discharge pressure 110, right? We might want to improve the system by going from modulation to load unload compressor, a brand new compressor, more efficient with 2,000 gallons of storage. Uh, rated pressure remains the same, I believe. Oh, no, sorry, rated pressure, that's the new compressor coming in, but we'll be running at 110 PSI. So some adjustment has to be done for lower power, right? So we reduce the pressure by 6%, adjust this fully loaded kilowatts based on that calculation. This would be the new power, right? Average savings, 80 minus 52, 28 kilowatts. The savings times 8760, assuming this compressor is running full eh, the full year, 245,000 kilowatt hours per year. So that is based on kind of a calculation like this, right? We can see that is not 100% linear. If we decide to, instead of a fixed speed compressor, go from modulation to VSD compressor using the same numbers as we had before, right? We can pick from the KGI sheets. We might have to adjust for pressure again because this compressor is tested at 125. We're running at 110, right? We adjust for power, and we pick from the KGI sheet. We might have to do some interpolation here. We come out to the new power consumption would be 41 kilowatts under the same loading conditions, right? 80 kilowatts minus 41 is 39 kilowatts, much higher than before, right? Because this compressor is more a one-to-one turn down and saves much more energy, right? In the 8760 hours operation. Now we might put in, say, a central controller or something to better control our compressors, right? That's another way to save on a compressed air system. So mechanism of saving, improve the efficiency of the air production, calculation method, determine load unload runtime. We could use the status method or calculate optimal compressor configuration, kilowatts per 100 CFM for each baseline. And that's one of the things that I very often use, right? I might calculate what the system kilowatts per 100 CFM is of the old system. And from the KGI sheets, if I had perfect control, I would calculate the kilowatts per 100 CFM for an optimized system and compare the two, right? This one might be very high, right? 40 kilowatts per 100 CFM. And I would know with perfect control, a new system with a variable speed drive compressor might be running in 18 kilowatts per 100 CFM. And then I could, I subtract one from another, and that's the possible savings, right? Quick and dirty method of estimating the possible savings, right? Pitfalls, theoretical savings that I just mentioned may not match actual savings, right? Sometimes for peaky loads and stuff like that, it's hard to perfectly control the compressors. Savings depends on compressor types and sizes, difficult to achieve full savings if the demand is highly variable. I just said that. Okay, so just a worked example, just based on these low duration curves, I can see the various unloaded portions in this system. And this big one, right? We already looked at this. This compressor is running unloaded for a long period of time. So I can even just, this is graduated in hours, right? I can figure out during that period of a day, right? What the number of hours for the unloaded portion of that might disappear with perfect control, right? Add them all up and multiply the savings by 365 days, right? And come out with 178,000 kilowatt hours per year with perfect control, right? Okay, an example project, cabinet making facility, right?
Ron,
Yeah, go ahead.
I'm butting in here just based on the time on the clock to switch us over to the question and answers. That said, if we don't have a lot of questions to answer, we will switch back to the cabinet making facility example. So you can kind of walk through that in a kind of a more entire project based worked example for compressed air savings. But with
Okay.
that, I wanted to open the floor just to in the hopes or in case people came with locked and loaded questions so that they'd have an opportunity to ask those. We had a couple in the chat that I can get us going with as long as I can find them. One was from Al Sutton at Toyota, who had to drop off and actually had two questions, one of which you answered in the course of the presentation, but I'll just maybe still come back to it to reiterate. He was asking when we were going through different methods for testing leak rate, if we could just, if it's possible to just measure or calculate and infer the leak rate from flow meter measurements. He used a fancy word. He said if we look at the asymptote of the curve, which I think is just as you're describing, if you look at normal operation, then you have a period of non-production and looking what that is. But maybe you can just go into a little more detail about what you would be looking for in a flow data series to ascertain the flow rate, or sorry, the leak flow rate.
Yeah. Yeah, if it's a shift-oriented plant with no production during periods of time, right, it's very easy to estimate what the leak flow might be if you know the conditions in the plant during the minimums of the peak flow. So like midnight Saturday night, right, there's nobody in the plant, right, there's 300 CFM flowing. It's pretty good bet that most of that is leakage, right? So, but it can be more difficult in a very large plant. Could be like Toyota, right, where production might never stop, right? So they might have to wait for Christmas or something like that to get a minimum for their leakage load, right? So it's knowing the characteristic of the flow and where the minimums might be, where there's absolutely no production, right? Uh, I'm not sure if that's a good answer to that question or
Yeah,
not.
I think it's a great answer. I think it's on one hand, it could be the most convenient way if you have a flow meter and you have shutdown periods. But if you don't have shutdown periods, you might have to resort to one of the calculation methods we shared earlier. Okay, Al's other question was when we were talking about operating hours and things that should be considered, and one of which was seasonal variations. And if I understood his question, to say, well, what if, in a system with constant operations, constant loading, is there any reason to expect seasonal loading? My answer in the chat suggested that that would depend on the intake air temperature to your compressors, would have some impact on efficiency, but I don't know if there's anything else you would add to that.
Yeah, when you're calculating the power baseline for a large system like Toyota, right? They'd have a bunch of centrifugal compressors, and yeah, those centrifugal compressors are affected by inlet conditions, cooling water conditions, um, ambient temperatures. So yeah, they would be less efficient during the summertime as compared to in the wintertime. Yeah, so it's when you're calculating an accurate baseline, you have to take into account those seasonal variations, right?
Yeah,
Another example, a food plant, right? They're making pizza pops. Uh, they sell more pizza pops in the summer, so this particular company that I looked at had an extra shift, right, during the summer compared to the winter. So if you want an accurate baseline again, you have to make sure that you're incorporating those extra shifts when they happen.
yeah, that's a great point, Ron. That season can mean sales season, like your
Yeah,
peak peak production season versus your
you bet.
um,
It could be
cold season.
temperature, it could be sales seasons, yeah,
Yeah.
or
You also made a
even
point.
production runs, right?
Yeah, you also made a point about centrifugal compressors in terms of that temperature variation, which maybe the buried point there is a difference when it comes to positive displacement, like rotary vane compressors in terms of their uh, the impact of temperature, intake temperature on their efficiency. Is that different than centrifugal machines?
Uh, well, back in the old days with the old reciprocating compressors, it did make a difference on the inlet. They would put intakes outside and stuff like that. It would be cooler, right? But with rotary screw compressors, it really doesn't make a difference, right? And you mentioned vane. I really don't think that it makes a difference, right? Bringing in air from outside, right? It doesn't really make a difference. The humidity makes a little bit of difference in summer versus winter, right? Because the water vapor is a partial pressure in the air coming in, right? And it condenses, right? It takes away a little bit from the efficiency of the compression, but really not all that significant.
Yeah, in that case, if you're with those kind of machines, if you're pulling really hot air from the compressor room, is it more of a maintenance concern, just a reliability with the compressors than
Yeah,
a,
to be overheating,
yeah,
overheating. Yeah.
okay, great. We're not getting a lot of questions, just means we answered them all. We anticipated them and built it into our materials. So with that, Ron, do you want to steal control of the screen back and we can go through the cabinet making example and then we'll just save 5 minutes at the end to wrap up. But I think that
Okay.
gives you plenty of time.
All right. Bear with me for a sec. Entire screen. Um, Hoping I select this properly.
You got it.
What do you think? Okay. All right. And this is just kind of a weird example that I like to show, right? Because it's going from modulation to uh, say variable speed compressor, right? Which gets you the maximum savings, right? So here's just a small little cabinet making machine facility, I should say, not machine. Uh, this is how it's laid out, right? Just a single compressor with a small wet tank and non-cycling dryer, right? So uh, we measure the amps, we measure pressure across the cleanup equipment, right? We want to see what the pressure differential is. And we're lucky enough in this tiny little place to have a flow meter, right? Which makes it a lot easier to calculate what savings would be. So here's a time-based chart, right? We can see it's a typical kind of cyclical um, operation throughout the week with no weekend operation and no midnight shift operation. We can see not a sawtooth waveform here, so that confirms that it's running in modulation, right? So very little change in the power consumption of this compressor for a lot of flow change, right? So the flow is jumping up and down, and what I did was I just put a moving average on top of it so we can see what the flow how the flow is changing over time. That red line on there. So I can take the data and I can sort it high to low for pressure, right? And if I did a pressure average through the full operation range, I'd come out to like a pressure of 50 or something like that. That's not the real pressure, right? The pressure is actually operating here, right? So we take the average, right? That pressure, it's operating at 102 psi, and it tells us about 50% of the time the system is operating. We can see the compressor amps, right? If we sort high to low again, we can calculate what the average is, 42.98 in this period, right? And we can see the flow, not very high, right? The flow for that 50% of the time, we can see the average flow, 30 CFM, right? So we can calculate a base case for the 4,200 hours it's running per year times the average kilowatts that we detected, 160,000 kilowatt hours. If we include the non-cycling air dryer, right, consuming 1.9 kilowatts, it adds to the baseline, right? And it's important to include the dryer, especially if you're going to do something about the dryer, right? It's extra savings, right, that are captured when we're doing the baseline. Total 168,000. And in this case, this calculation was done in Manitoba, so it mattered to the operating cost what the peak was, right? Because in Manitoba, they have a peak and energy component to the electrical bill. And we can calculate the specific power. And this is always what makes me shake my head about modulation compressors, right? 123 kilowatts per 100 CFM is the operating specific power of this system. So extremely inefficient system should be in the 20s for a small system like this, right? Not 123, right? So that tells us we've got massive amount of savings possible in this system. So we might choose a small variable speed drive compressor. We pick off the KGI sheet of that compressor. We know what the flow is, the average flow, so we can pick off what the kilowatts are going to be for that compressor based on that flow. And we come out to 4,200 hours at 8 kilowatts. That many kilowatt hours. This should be kilowatt hours. And we might reduce the pressure some, right, from 102 down to maybe 95, who knows. We might put in a cycling dryer, right? So this cycling dryer, because it's lightly loaded, would only consume 0.2 kilowatts, right? So we can calculate what the predicted baseline for a new system with a variable speed drive and a cycling dryer would be. The peak is greatly reduced, and the specific power, including the dryer, is around 28 kilowatts per 100 CFM. It's not that great when you compare with large compressors, right? Large compressors might be operating down in under 20, but with the smaller compressors, they're not as efficient, but quite a significant change to the previous specific power, right? Okay, is this where you're going to take over again?
This is. I will jump
Okay,
in and I will switch to my screen. But
okay, very good.
thank you so much, Ron. So I hope everyone enjoyed themselves on this session and learned something. In wrap up, just want to remind people, where we started with just some good practices, methods to apply when approaching a savings estimate for your energy saving project or compressed air energy savings project. So we talked about considering the accuracy that you need, looking at the data that's available to you, always starting with an accurate baseline or the most accurate baseline you can develop before getting into your savings estimate. One of the key considerations around that baseline is not just the power measurement, but considering how your system operates over the course of the year. Ron talked about this in detail, and it kind of came up in the questions, looking at the seasonality, the weekends, the downtime. Some of these are known items that you can use to improve your estimate without actually even having to measure. Measurement is better, but if you have an idea of when your facility is shut down, use that information to improve your estimates. Understanding the savings mechanisms helps with your understanding as well as identifying potential opportunities. And then I think we've kind of covered with these estimates, where there are limitations when we're using, let's say, rules of thumb or approximations as opposed to actual measurements. Tips and tools that we hope that you're taking away with you is the availability of the CAGI data sheets if you weren't aware of them, but in all likelihood, most of you were. But hopefully you just picked up some tips on how those sheets can be made most useful and the importance of making sure that you're adjusting for the discharge pressure. Another point, and kind of comes back to that limitations, is making sure you understand the appropriate, like when you're using specific power to calculate savings, making sure you're using the effective specific power as opposed to just the rated specific power of that compressor or the system. We went through some examples of estimating the flow from, as an example, from compressor status when you don't have other data available to you, and then some leak estimation methods and multiple different approaches for savings calculations, from improved efficiency or a more efficient compressor, VSD, controls changes, pressure reduction, leak repair. So hopefully if you've already got the ideas for how to save energy, this is going to help you walk away with some ideas for how you can quantify those and wherever you're at in that project, get to the next step. As we mentioned throughout, you can refer to your participant workbook for some additional references and examples to support these methods, tips, and tools. There we go. Skip over the Q&A because we already did that. Just wrap up with some additional resources. So today's session really focused on understanding and doing your own calculations, since we believe that fundamental understanding is critical for any energy professional. However, there are some great tools out there, including Canada's own RETScreen tool. The team there has invested a lot of effort into improving their compressed air calculator and other tools and functions within the RETScreen suite. So yeah, this is one tool available made available by NRCan. I'd love to hear in the comments if anyone has experience using this tool and if they have any thoughts, opinions on the uses or limitations. Please type that into the chat and let us know if you've tried this tool out. Additional resources, lots of good reading material and other references available from the Compressed Air Challenge, which I would suggest is kind of the definitive, most comprehensive online resource of compressed air information, particularly like for all kind of facets of compressed air systems and operations and maintenance, but equally so when considering energy savings opportunities with compressed air systems. So often you'll even see, the example on the left there is a DOE publication, but if you look at the bottom right corner, the actual source material is coming from the Compressed Air Challenge. So that, yeah, that's the one-stop shop. But speaking of the DOE, and similar to NRCan, they've developed their own suite of energy tools, calculators. So the Measure is their latest iteration of this suite of tools, which includes a compressed air. I'm going to call it a compressed air calculator, but it's multiple calculators, and there's definitely a compressed air module in there. Ron, I think you've used that or at least played around with it.
Yes.
And yeah, it's definitely worth checking out for compressed air and other tools as well. I think I'm proud of what we've done here in Canada with RedScreen, but I wouldn't stop you from checking out what else is available out there.
Yeah,
All
it's
right.
very good tool.
Great. Yes, that is what I've heard as well. All right. In addition to those tools, there is other expert support available through Save on Energy. So if you have questions that come up after this session that occur to you, you can post those on the Energy Manager Learning Platform if you're already registered with that. In addition to the forum, you can also reach out and get advice, coaching, and support for the items listed there. If you're not on the learning platform, we've got a QR code in the bottom right. You can scan that. And one thing I'd be remiss if I didn't mention is that the learning platform includes a variety of energy management training courses, modules, one of which is on compressed air optimization. So if you're thinking to yourself when Ron was covering those fundamentals that you could use a little more of a brush up on compressed air fundamentals, I highly recommend that course. All told, it's a handful of modules. In total, it should take you about an hour to go through. So a good quick blast of compressed air knowledge or brush up, if you will. Speaking of compressed air training opportunities, there are training incentives available from Save on Energy. 50% or up to $750 in incentive for training such as fundamentals and advanced management of compressed air systems. These are compressed air challenge training courses. We mentioned Ron is a facilitator for the compressed air challenges training. And as it happens, there's actually one happening tomorrow that Mr. Ron Marshall is leading. So if you got a taste today and feel like you want to do a deeper dive tomorrow, you can look for that. It's presumably posted on the Save on Energy training support, but it might not be if it's not associated. I don't know if you know, Ron.
I don't think it is.
Okay. You
Yeah.
can find it on, it's a CIET.
Yeah.
Okay,
If you
so it would be
go
on.
to their website, hopefully the registration is not blocked, but I'm sure you could talk to them and get in. If you looked at compressedairchallenge.org calendar, right, there's other sessions throughout the year that could be something that people could take as well. And says on the website, IESO website, that 50% rebate could be gained from anyone in Ontario. So
Absolutely. Okay, and that is basically it. If anyone wants to just on their way out, tell us what's one tip from today that you will apply when estimating savings for compressed air projects in the future. We'd love to hear it. And otherwise, have a great day. Or if someone has a question, also, we've got a couple of minutes. So the world's your oyster. But otherwise, it's been great having you here today. Hope you got some valuable takeaways.
yeah, very good. Yeah. So I see one chat. great presentation. Real-time data is key, especially